Last week, we looked at double integrals and polar coordinates. So now we're going to look at different coordinate systems for triple integrals. There's two we're going to check out: cylindrical and spherical. Cylindrical, not much to it really. It's basically polar plus a z dimension. And then spherical, a little more involved than that. First, this is 12.6 from Stewart. So cylindrical coordinates, we have r, theta, and z. So relationships would be x is r cosine theta, y is r sine theta, so exactly the same as what you see in polar, and z is, well, z. So going the other way, we have the same relationships as going back the other way. So we have a definition of r in terms of x and y, just the magnitude, and then tangent theta is y over x. All right, so once you know polar, then you're good to go with cylindrical. Okay. So, for instance, let's suppose we have this point, x, y, z is minus 3, 3, and 4. So we want to go from x, y, z to r, theta, and z. So r is just going to be square root of x squared plus y squared, square root of 18. Okay. So actually the only really interesting thing about this conversion is for computing theta. So we have tangent theta is y over x, which in this case would be minus 1. So this is something that you have to be careful about. What is theta?
It could be several, right? Or is there some sort of confines that we're looking at?
There is a rule that indicates which is the right one.
Okay.
So, so what you need to do is keep in mind x. It's all about x. So in this case, just looking at x and y, minus 3, 3. You're over here. And then z is coming out of a board. So, on the other hand, if you put in arctangent of minus 1 on your calculator, it's going to give you minus pi over 4, which is down here. So, you should remember, hopefully, from Calc 3, what you do in that case, how you correct it. That is one way to look at it. They just go through the origin and come out the other side. And how you correct numerically what you do, you add pi. So that accomplishes the same thing. So it'll be 3 pi over 4. So when x is positive, it's just the arctangent. When x is negative, it's the arctangent plus pi, and then when x equals 0, it's pi over 2 if y is positive, minus pi over 2 if y is negative. So that is everything. The only case that's not covered up there is when x and y are both 0, in which case you don't really have a theta. Any theta would work. R would be 0. You would be at the origin.
Now, I can understand why there'd be more than one answer for the tangent of theta, but why is it necessarily that negative pi over 4 is not the answer?
Oh, because, so what can happen is, when you have a tangent, whatever, actually, regardless of the sign of y over x, in this case it's negative, you don't really know from a ratio alone whether it's y that's negative or x that's negative.
All right.
So depending on which one it is, you could be up here or down here.
Okay.
So that's why you use x to settle which angle it is.
So that's why you added the pi?
Yeah, because our tangent, the range of our tangent is minus pi over 2 to pi over 2.
Right.
So your calculator's arctangent just assumes that x is positive. So that's why if x is positive, you can just accept what it gives you. Otherwise, it jumps to the wrong conclusion. It's really x is negative and y is positive, so you need to correct pi. Also, if you have a point over here, your calculator will put you up here. So again, you add pi. Yes?
So are we going to add pi in all cases?
Only if x is negative.
Okay.
Yeah. And so in this case, that is our theta. It's going to be 3 pi over 4. So our cylindrical coordinates, we have our r, 3 root 2. We have our theta, 3 pi over 4. And z was just the z that we had, it's 4. So those are cylindrical coordinates of that point. When it comes to evaluating integral, if we have a function of x, y, z, we need to integrate it over some three-dimensional solid. You might find it more convenient to convert to cylindrical coordinates, just like in the 2D case, it was sometimes more convenient to work with polar coordinates. So I'm going to describe this region. So we have a paraboloid. Z is equal to x squared plus y squared. So we have a solid that's bounded below by the paraboloid, and it's bounded above by this plane, z equals 4. So it's what's contained within here. And we're just taking, we're not taking the whole thing. We're going to take just a portion of this. So it's just this part that I'm shading here that is in the part where y is positive. So now what I've said in the notes is it's bounded by the planes y equals 0, it goes down the middle, and then y equals 2. So here's y equals 0, and here's y equals 2. Y equals 2, that plane meets this edge. Right. So I'm just using that as a guide to indicate which portion of this we're wanting to integrate over. Right. So if you think of just this big bowl that we're just chopping it in half, we're taking this half that's in the front, if you will. If we were to look at this a little differently, different angle, so here is z, and here's y, and then the x-axis is coming out of a board, then this is what we're looking at. So this is z is equal to x squared plus y squared. So this is the section corresponding to x is equal to 0. And here is a vertical line y equals 2, so this is a plane y equals 2 coming out of a board. And the plane y equals 0 is coming out of a board over here. So this is a side view looking down the x-axis. A top view, so now the z-axis is coming out of a board. Right, so we have x and y. Then all we can see looking from the top, so it's just this portion is what we care about. At the top we're looking at x squared plus y squared is equal to 4, because the plane z equals 4 marks the top of a solid. So looking from above, this is what we see, and this is the part we care about. So we're only integrating over this half of the solid. So this is what you got to do, of course, with triple integrals. You got to be able to try to visualize the region that you're going to integrate over in order to come up with the proper limits, or determine whether you want to just do it in terms of x, y, z, or maybe convert to other coordinates. So what are we going to integrate over this region? Well, I'm going to make that part easy. We're just going to compute its volume. We're going to integrate f of x, y, z is equal to 1 over this solid. And you might think, oh, that's going to be an easy integral. Alright, so to integrate 1 over this half paraboloid, if you will, the way we can describe the limits in terms of x, y, z are as follows. So our innermost integral will make with respect to z. So the solid is bounded below by z equals x squared plus y squared, so that is our lower limit. Our upper limit, well, the solid is bounded above by the plane z equals 4, so 4 is our upper limit.